Hi, welcome to this new learning series. This is designed to develop a quick understanding on 5G architecture and key principles. In this learning series, we will give you some high-level overview on 5G technology. We will start with a brief history of telecommunications. Then we will understand that what are the needs to develop more advanced technologies like currently in 5G and in future 6G or 7G and so on. We will understand that what is the necessity and how 5G can be used in various applications. Then we will see the most important building blocks of the 5G radio access networks and 5G core networks, which plays the important role to fulfill the wide use cases of 5G. If you're already familiar with 4G technology and may be curious that what 5G comes with as an enhancement compared to the 4G technology, or maybe you are already working with certain aspects of 5G but wanted to expand your understanding on the other aspects or other areas, or if you are completely new to the telecom field and wanted to explore the telecom world, no matter where you are on your learning journey, we are here to take the next step together as we will explore the fundamental principles of 5G in this learning series. The purpose of this course is to deliver the concepts of important fundamentals and key principles which are evolved in 5G systems. We will also understand that what new techniques are introduced in 5G to cater the wide use cases of 5G. So let's get started. We will begin with a quick overview from the history of telecommunication. Because if you do not understand the past, you may not connect with the current evolutions and future demands. So it is important to understand, but we will not go in deep. So in the era of 1900, landline phones was common around the world. That was the first step in telecommunications. By 1930s, the first mobile phone was invented, and that actually have wireless support. And that was the start of wireless domain, generally called as 0G. These mobile phones were using a very basic features, that is push to talk. So the communication happened through a two-way radio connections between a network and a car-mounted transceivers. At that time, we have huge transmission towers and they cover large areas. It is near around 20 miles in radius, and that area was called mobile service areas. Frequency reuse concept also started to use at every 100 miles. But the key challenges was that service providers had to manually connect the calls to the regular phone networks. So operators have a lot of manual monitoring, and they also manages the channels which are being used for communication. So it was another challenge. Those communications was started from 36 MHz band, and it hardly have 10 to 30 channels only. Means those systems can only accommodate very few users. Now during 1970s and early 80s, the demand was increased and user had to wait for their turn to get the mobile services. And surprisingly, that waiting list reaches up to 3 years of waiting period. And that shows the demand, that why we are needing the advanced wireless telecommunication systems. Now in 1980s, Bell Labs introduced AMPS, that is Advanced Mobile Phone Systems. This is also known as 1G or first generation of cellular telecommunication. This new technology allows simultaneous talking. So we moved from push to talk kind of system to the AMPS system, and that was a great improvement from the previous generation. 1G also introduced automatic channel selection, so things gets easier for service providers. This innovation was the base of wireless communications, and now more people can experience a true mobile communications. AMPS uses analog technology, and it was using frequency division multiple access or FDMA. So each communication happens over a separate 30 kHz frequency channel. Now the another problem is bandwidth requirement, because now more users are expected to use mobile services. So to fulfill that need, FCC allocate the frequency spectrum from 824 MHz to 894 MHz. So this bandwidth can accommodate around 666 channels. Another important advancement was in coverage area. Now because AMPS started to use hexagonal cells to serve the mobile service area or MSA, instead of using one single cell to serve circular radius in previous technology. Also, those 666 available channels were distributed between 7 cells, and each cell having its own set of channels. Now these 7 cells collectively using 666 channels, and then frequency gets reused for additional set of 7 cells. This concept was the origin of cellular communication. However, AMPS technology has many challenges like poor voice quality, shortened battery life, bulky devices, unreliable handoffs, and weak securities, etc. So, when the rollout of AMPS was started, just soon after that, new innovations get started on digital cellular communications. And in 1987, 13 European countries agreed to create a common cellular telephone systems across the Europe, which refers to the GSM specifications from ETSI. And then GSM was commercially launched in Finland in 1991. GSM was using TDMA and FDMA based multiple access technologies, and because of this advancement, it allows more users to serve from the same resources. TDMA or time division multiple access is the concept where different users share the same frequency resource but at different time slots. Those digital systems also supports new services like texting and even picture messaging, although they were at the very low speeds. This was further evolved by introducing a new domain called as packet switch domain. This was an addition to the circuit switch domain, which is sometimes referred to as 2.5G or EDS. This offered better services to the end users, and now they can use it for more services like sending emails, receiving emails, etc. And even web browsing was possible at a speed of 64 kbps to 144 kbps. In 2008 or 2009, LTE was introduced, and now it was a fully packet switch technology, and that was the start of 4G. It is interesting to note that each generation of technology is sometimes referred by the name of radio access technology behind the generation. For example, 3G is known as WCDMA, and 4G is called LTE, and 5G is called New Radio (NR). 4G supports the bandwidth from 1.4 MHz to 20 MHz. 4G uses OFDMA technology in the downlink and single carrier FDMA in the uplink. OFDMA is a multiple access technology where a wideband carrier is splitted into many narrowband subcarriers, and they act as an individual channels. And because of that, we can have wideband data rates that offers high data rates and throughput. At the same time, we can also use the benefit of better propagation characteristics from narrowband channels. 4G offers good broadband data rates, and because of that, it generally referred as the generation of mobile broadband. As an advancement in 4G, it also introduced different new concepts to even boost the data rate. For example, multi-antenna systems and carrier aggregation techniques, etc. It also enabled new services like high-definition mobile TV streaming, mobile gaming, etc. Now, as technology evolved and new services offered, as a result, more and more devices were started accessing the mobile internet, and it is still growing in the present time as well. So, to meet those growing demands and to cater such huge number of devices and users, we are needing more advancement, and hence we are needing new generation of systems. And hence 5G standards started developing, and it is still evolving. 5G supports up to 400 MHz of bandwidth, and it is huge. 5G continue to use OFDMA based air interface. In this course, we will be discussing majority of the key components that contributes in 5G. We will be talking about why 5G is needed, and we will understand that why 4G is not enough to cater the future requirements and what are the 5G use cases. So why 5G is actually needed? To answer this, let's explore some key trends in the telecommunications. First, let's consider the number of mobile subscribers. The number of mobile subscribers are increasing rapidly. In 2018, when there was a global population of 7 billion people, there was already 8 billion mobile subscriptions, and those numbers are actually growing very fast, and they continues to increase in 2024 as well. Alongside this growth in subscriptions, the amount of data which is being consumed by subscribers is also growing very fast. So this creates a strong need for a network that can handle this massive traffic in more efficient way. Additionally, the number of IoT devices or Internet of Things connections are increasing rapidly. So it's not just people who are connecting to the internet, but machines are also joining. So in the upcoming years, the number of connected devices is expected to grow by 4 times from now. So to address this huge expected demand, there is a group called MATIS Group or METIS Group. This is Mobile and Wireless Communication Enablers for 2020 Information Society. They outlined the requirements for a new network concepts during 2013. So our new developments and new concept must align to meet those technical goals which are set by MATIS. These goals were set in 2013 and they are related to the future network performances. This includes supporting 1000 times more mobile data per area. The new network should also support 10 to 100 times more connected devices. New network systems should also offer 10 to 100 times faster data rates for users. Another goal was to achieve 10 times longer battery life for the low power devices, especially for the massive machine type communication related devices. They aim to reduce the latency by 5 times, which will improve the end-to-end communication speeds. Most importantly, these improvements must be achieved with the new technology without increasing cost and energy consumptions compared to the 2013 levels. Other organizations in the world of telecommunications also have similar vision for the future. For example, here is a vision from 5GPP for the future, where not just people but entire cities or infrastructures, homes and devices are fully connected with each other and they will empower their maximum potential. And this brings us to the question that what exactly is 5G? Well, I will say that 5G is not just one technology, but it's a collection of technologies which are designed to deliver the advanced network performance, which we have just discussed, and it supports a wide range of new use cases. 5G introduced a new air interface called New Radio or NR, and this will work along with a completely new network architecture. New concepts were also developed like network slicing, massive MIMO, bandwidth part, numerology selections, and many more new things. Okay, so now let's move to the 5G use cases. But before this, we need an overview that how exactly 5G will be used and how does it differ from the 4G network. In the starting, 4G mainly supports mobile broadband, which allowed us to do things like checking emails, browsing the web, streaming videos, and listening to music, downloading contents, etc. and this kind of stuff. But 5G expands on this by introducing four major categories of use cases, each use case offering new possibilities beyond what 4G can do. The first use case is enhanced mobile broadband, which is most straightforward. As people continue to use more broadband services, 5G will enable even higher quality experience like streaming 4K and 8K videos and even 360-degree videos, watching virtual reality contents and augmented reality contents, playing or streaming video games, etc. And all these with faster speeds and more reliability. The second use case is fixed wireless access. Well, 50% of the world's population is still waiting for a reliable broadband and internet connections, and they are still depends on the fixed wired connections like fiber at home, etc. This is particularly in a suburban and rural areas. 5G can help us here by allowing telecom companies to use their existing cellular infrastructures to deliver broadband and high-speed internet services to those users, of course with more reliability. For example, here you can see a typical scenario where the spectrum assets owned by some operator is underutilized in suburban and rural areas. They can use this unused spectrum and existing sites to provide a fixed wireless access through a device called CPE. This is Customer Premises Equipment. This device connects to the 5G network and offers Wi-Fi or Ethernet to the home devices, just like a Wi-Fi hotspot device. And this can become the main source of internet in the future. Hence, fixed wireless access also provides an additional way to generate revenue for the telecom operators on top of their mobile broadband revenues. The third use case is massive machine type communications. You may think about the sensors that are installed in your vehicles or homes or offices, and they capture the relative informations and sends to the host or communicating with each other Or maybe they installed in vehicles and track the location of your device. Or think that these sensors are set up in your garden and monitors the environmental conditions like humidity, wetness of soils, sunlight, etc. These sensors send a small amount of infrequent data, so we can control the power consumption of such devices. And the expectation from such devices is to have a long battery life, like many years from just a couple of batteries. This category of devices are expected to be in huge numbers in future, and 5G is designed to handle a large number of those devices within a single area, which make it perfect for smart cities, agricultural areas, and other applications where many devices need to communicate with each other. The fourth use case is ultra reliable low latency communications. To understand this, take an example that there is a surgical robot in a hospital and one surgeon is controlling that robot from a remote location. Then the connection between these 2 points plays very important role. So during a surgery, the connection needs to be extremely reliable with no downtime, because even a small interruption in the connection can disrupt the whole operation. Secondly, the network also must have very low latency, so there would be no delay in the robot response. This type of communication is essential for critical applications like remote surgery or self driving cars, etc., where reliability and speeds are very crucial. Because it will be very difficult to perform a surgery when the robot has a huge lag from the controlling point. This kind of applications are called ultra reliable low latency communication, and this type of communication will also serve by 5G. In conclusion, 5G is designed to serve different use cases. These are beyond from the mobile broadband use case, so 5G going to handle some very fascinating and challenging use cases in future. 5G is not just about faster mobile internet, but it opens up a wide range of new and exciting possibilities, from enhanced mobile broadband to support a vast number of connected devices, and even it will enable to support critical applications like remote surgeries and self-driving cars, etc. In the last session, we understand the need of 5G technology and its advancements, and we also talked about the variety of use cases which are planned to serve by 5G technology. Now, in this session, we will be briefly talking about the 5G systems and control plane and user plane and curves in 5G. Okay, so before reaching to 5G, we should see that how 3G and 4G systems was look like, and then we will compare that in brief with the 5G systems. So this is how the 3G systems looks like. 3G systems had three main sections: the user equipment or UE like smartphones and modems, the radio access network or RAN, which is also known as UTRAN, UTRAN. This is responsible for wireless access through the components like Node B and the RNC, radio network controllers. And the last section is core network, which consists of different functions like storage of subscriber data, security, policy management, mobility management, etc. Well, I'm not going deep on these components at the moment. This is just a brief section. Now the 4G system, this also looks similar, like we have user equipment, one radio access network which is called EUTRAN in 4G, and it includes eNode B, and one core network, this is known as Evolved Packet Core or EPC core. This EPC or Evolved Packet Core also handles similar functions like 3G core, but with little more advanced capabilities. Now continuing the trend, the 5G network also consists of user equipment, the radio access network, and the core network. The 5G user equipment includes 5G enabled smartphones, laptops, tablets, modems, Internet of Things devices, and even 5G routers for fixed wireless access. The 5G radio access network or 5G RAN includes G-Node B, which supports the new radio interface called NR. In some cases, you might also see NG-Node B, which supports both NR and LTE technology. The 5G core network has the functions like storing subscriber data, mobility management, session management, etc. The defining aspect of the 5G core is that in 5G core, there is a clear separation of control plane and user plane functions, and that allows more efficient and flexible network operations. The 5G core is designed with the modern software technologies, including service-based architecture and network virtualization, which make the network more adaptable and scalable. So as mentioned, separation of control plane and the user plane is the one of the key principle of 5G architecture. So what is this control plane and user plane separation? Let's understand this with one example. Consider in some 5G use cases like massive machine type communications, there are many devices that sends a small amount of data. When these devices are dominating in some network area, then there is a need to scale the control signaling infrastructure to handle them efficiently. On the other hand, we have mobile broadband devices, and these devices create a large demand of user plane functions compared to the control signals because this handles more data flow. And if these devices are more common in some network, then the user plane needs to be scaled up rather than the control signaling. So if there is no separation of control plane and user plane functions, we would have to scale both functions together, even if only one of them needs it. And this would be an inefficient way of integration because it may create the wastage of network resources. By separating the control plane and user plane, we can scale each one based on the network's specific need. Separating control plane and user plane also helps achieving the lower latency, which is crucial for 5G applications. This is the diagram of 4G system. So you can see that 4G system with the indication of control plane and user plane traffic. You can see that the control plane traffic marked in green and the user plane traffic is in orange. In the 4G system at the top, both the serving gateway and packet gateway handles control plane and user plane functions, means it handles both of these data. But in the 5G core at the bottom architecture, the control plane of serving gateway and packet gateway are combined together with parts of MME to form the session management function shown here as an SMF. The user plane of serving gateway and packet gateway forms the user plane functions, indicated here as UPF. This separation of control plane and user plane functions is known as CUPS, which stands for Control and User Plane Separation. In 5G, the mobility management functions of the MME evolved into the access and mobility management functions, normally called as AMF. The HSS becomes user data management or UDM, and the PCRF turns into the policy control functions or PCF, and all together they form the 5G core. Now in this session we will be talking about 5G deployment options. So the question was that when 5G deployment will start, then how the network structures will looks like. So let's begin with 4G. In 4G deployment, the radio access network or RAN works with a 4G packet core or EPC core. This setup is known as option 1. Ideally, a 5G deployment would consist of a 5G RAN network which is connected to a 5G core, and this architecture is referred as option 2. However, the network cannot have that straight transition from option 1 to option 2. So in reality, 4G technology and 5G technology will work together in the system and they will complement each other for a reliable network, at least for the few years after 5G deployment starts in. So you also see in present time that 4G and 5G RANs are working together in a setup called dual connectivity, or generally referred as non-standalone network. In dual connectivity, the user equipment or UE communicates using two radio access technologies simultaneously. In dual connectivity, one radio access network technology serves as the master technology and the other act like a secondary technology. And the secondary RAT can either forward the traffic to the primary RAT or it can send it directly to the core network. The important note is that the control plane signaling can be only managed through the primary RAN. If LTE connected to the 4G core is the primary radio access technology and the new radio or NR is serving as a secondary radio access technology, then this setup is called ENDC or option 3. This configuration is especially useful when NR coverage is spotty. Wherever NR coverage is available, then the network can utilize NR or 5G performance by using it as a secondary carrier. In the later stages of 5G, when NR gets its full coverage or wider coverage than the LTE coverage, then NR can be used as your primary radio access technology, which will be connected to the 5G core. And then the LTE will act as a secondary radio access technology. then this setup is known as option 4 or NEDC. Also, in future stages, while some 4G phones are still in use, or when 5G UE is in the location where there is only 4G radio coverage, then LTE could be used as a radio access technology but with 5G core. Then this is called option 5 or ELTE. ELTE is evolved LTE. That simply means that LTE has been upgraded to support the 5G core interface. In addition, when LTE is used as a primary radio access technology and NR as a secondary radio access technology, but they together with the 5G core, then it is called option 7. So the options with one single radio access technology, like option 2, are called standalone networks. And the options with two radio access technologies are called non standalone networks, most commonly the option 3. Now let's focus on the 5G radio access network or 5G RAN. Compared to the LTE air interface, the 5G air interface should meet main two requirements. First, it must efficiently utilize the new spectrum, which also lies in the millimeter wave band. Second, it needs to support the various new use cases introduced in 5G. This leads to the development of a new wireless access called NR or new radio. In the 5G ecosystem, NR will not be the only wireless technology. Instead, it will work together with other wireless technologies such as LTE. In the new 5G designs, there are many enhancements that caters to the different goals of 5G. For enhanced mobile broadband, 5G also introduced some new concepts such as massive MIMO, beamforming, wideband carriers, and carrier aggregations, etc. Also, to support the ultra reliable low latency use cases, 5G included new features like flexible numerology, preemptive scheduling, and grant free uplink access. To improve the cost efficiency and flexibility, there are new concepts like virtualizations. So, starting from this session and in next few sessions, we will explore these defining features of the 5G radio access network and we will know that how they function. Let's start with MIMO. So the question is, how can we use the advancements in the antenna technologies to improve the capacity and the data rates in 5G? Let's begin that by exploring the evolutions of MIMO technology first. So at very beginning, omnidirectional antennas were used. They offer broad coverage, but that is uniform coverage. You can see in the top left picture, we have antenna which is providing uniform coverage in that radius. Then it was realized that the capacity of the network can be improved by using sectors, which brought the coverage like this, like at the bottom right section here. So you can see that this approach creates three different cells from a single base station. Now we can further enhance this by directional beams, more precisely to a specific user equipment or UE or some directive points. This is where beamforming comes in picture. But before learning about massive MIMO, we have to understand the basics of MIMO. In a single input and single output system, which is generally called as SISO system, we have one transmit antenna. The signal passes through a feeding channel and reaches to the single receiving antennas. Now, in this step, and according to the Shannon equation, the capacity of this system can be enhanced by either increasing the channel bandwidth or by improving the signal to noise ratio or SNR at the receiver side. Now, if you have multiple transmit antennas and a single receive antenna, then this configuration is known as multiple input, single output or MISO system. And in this setup, if the antennas are placed at least at the half of the wavelength, then each transmit antenna creates an independent feeding channel to the receive antenna. This phenomena is known as transmit diversity. Now, when the same data sent through these multiple channels, then they are affected by their independent channels. And by combining these received signals at the receiver, the signal to noise ratio or SNR gets improved, and that enhances the channel capacity. This approach is especially beneficial for downlink because the multiple antenna setup requires more space, so they can easily locate it at the base stations. In a similar fashion, if there is a single transmit antenna and multiple receive antennas, then we also achieve independent feeding channels. This is called receive diversity, and it also enhances the received signal to noise ratio or SNR by combining the effects of different feeding channels. In this setup, the signal processing occurs at the receiving end. Now, when the multiple antennas are used at the both end, means at the transmitting end and at the receiving end, then this is referred as MIMO or multiple input, multiple output setup. And when there are at least 16 transmit antennas and 16 receiving antennas, then it is often called as massive MIMO. However, some says that the minimum number of antennas for massive MIMO should be 32 antennas or more for each side. Now, MIMO offers three main methods to enhances the data transfer rate. First, when signal to noise ratio is low, then the diversity techniques can be applied to improve the signal to noise ratio, just like before. However, if signal to noise ratio is high, then spatial multiplexing can be used to increase the data rates and system throughput. In spatial multiplexing technique, throughput is improved by transmitting multiple data streams simultaneously over the channel. Now there are two variants of spatial multiplexing. First is open loop spatial multiplexing and second is closed loop spatial multiplexing. In open loop spatial multiplexing, the transmitter does not require channel state information. However, it is less efficient than the closed loop spatial multiplexing. In the closed loop spatial multiplexing, the transmitter receives the channel state informations through the feedback from the receiver. And with the knowledge of the transmitter, appropriate precoding is done in the transmitter and processing is done in the receiver side. This allows the data streams to be separated effectively. The maximum number of streams in such MIMO systems is limited by the minimum number of the either transmit antennas or receiving antennas. Now, if all the received antennas belongs to the same UE, it's known as single user MIMO, like you see in the top section of this picture, where all the receiving antennas belongs to the same UE. So it is called single user MIMO. Same way, if multiple streams belongs to the multiple UE at receiving end, and these simultaneous streams received by different UEs at the same time, then this setup is called multi-user MIMO, like you see in the bottom section of this picture. Now, this is the third MIMO technique, where the same signal is transmitted from each transmitting antenna. But these signals are phase shifted, and the phase adjustment is done in such a way that the signal power is maximized to some specific point where the UE is receiving the data. So this process is known as beamforming, which can be implemented in three different ways. The first method is analog beamforming. In analog beamforming, the phase of individual antenna signals are adjusted in the radio frequency domain. This adjustment influences the radiation pattern and the gain of the antenna array to provide the enhanced coverage. In digital beamforming, which is also called as baseband beamforming or precoding, this signal is precoded during the baseband processing before the RF transmissions. Means the processing occurs in the frequency domain. As a result, different signals are transmitted from each antenna. These are represented by different colors in this picture here. And the third is hybrid beamforming, when both analog beamforming and digital beamformings are combined. This technique is referred as hybrid beamforming. Beamforming enables the concentration of power towards a specific spatial region or specific UE. So you see in this picture here. As a result, now the scheduler has an additional responsibility because now it has to plan not only the time domain and frequency domain, but also the spatial domain. So this is how the beamforming works in 5G. LTE and its evolutions supports different forms of MIMO, like transmit diversity, spatial multiplexing, multi-user MIMO, etc. But in 5G NR, since there are spectrums in the millimeter wave bands, and as a result, the antenna size reduces significantly with such increasing frequencies. So it is easy to place many number of antennas in some form of array and place them together in one small package. So this huge array of antennas transmits narrow beams. And when the power from the different antennas combine in one direction, it acts like a strong beam. So this is the concept of beamforming. So in beamforming, the phase of the transmitting signals is adjusted in such a way that it adds a power in some specific direction to form a beam and eliminates each other power in the other directions. So that was one thing. But we also consider that millimeter waves have poor propagation characteristics. So for millimeter frequency bands, beamforming is important to serve 5G users. So here is a quick summary on what are the key benefits of using massive MIMO in 5G RAN. Number one, massive MIMO systems have a larger number of active antennas elements. Number two, massive MIMO allows for more focused energy to improve signal strength. Number three, high intensity beamed signals are less impacted by interference, so it has better signal quality. Number four, in good SNR conditions, more special multiplexing layers are possible, so you can enhance the data transmissions. Number five, massive MIMO improves the cellular network throughput and coverage. Number six, massive MIMO can serve more users simultaneously. Number seven, massive MIMO supports two-dimensional beamforming, so it offers better signal precisions in both horizontal and vertical planes. Now, in this session, we will be talking about 5G spectrum. So, spectrum plays an important role in a wireless communication. So, first, we will understand that what innovations 5G brings in terms of spectrum utilization. Here, you can see that 5G NR spectrum options are divided into two frequency ranges. First is FR1 or frequency range 1, and second is frequency range 2 or FR2. Frequency range 1 or FR1 includes the bands which are below 6 GHz and having the carrier bandwidth from 5 MHz to 100 MHz. So bands in frequency range 1 or FR1 have lower frequencies which provides better propagation characteristics. So they are ideal for coverage from macro base stations. Frequency range 2 or FR2 covers the band which are above 24 GHz and they can offer channel bandwidths between 50 MHz to 400 MHz. However, FR2 bands have poor penetrations through obstacles like walls, buildings, etc. But they can offer larger bandwidth. So these characteristics make them suitable for high density locations and hotspots such like city centers, stadiums, etc. Now let's see that how the spectrum utilization evolves over the time. Here you can see the allocation and the utilization of a spectrum over time. Green one indicates the 4G and blue one indicates the 5G here. Initially, a significant portion of a newly allocated spectrum is dedicated to 5G. But over the time, more spectrum from the existing 4G spectrum will be reformed to use for 5G. And this will allow us to get the benefit of higher spectral efficiency from 5G NR radio. So it's important to understand that 5G NR brings higher spectral efficiency through the different mechanisms. Let's look on two of them now. First, in this example of 20 MHz spectrum, LTE has 100 subcarriers and each of them is 15 kHz wide, whereas NR can accommodate 106 subscribers from the same 20 MHz bandwidth at the same 15 kHz spacing, and this happens due to reduced guard bands. Additionally, NR uses new channel coding options. While LTE relies on the turbo codes, NR uses low density parity checks codes or LDPC codes, which are significantly more efficient, especially for the large transport blocks. This makes them ideal for the data channels. Secondly, NR also employs polar codes, which offers about 0.5 dB gain over the turbo codes, which make them suitable for the controlled traffics. NR supports wideband carriers, which offers up to 100 MHz of bandwidth from bands below 6 GHz and up to 400 MHz from the bands which are above 24 GHz. These bands can also be aggregated through the carrier aggregations to achieve even higher data rates. In phase 1 of 5G NR, operators can aggregate up to 16 component carriers and up to 1 GHz of total spectrum to be utilized. And these component carriers can be contiguous non-contiguous, intraband, and can be intraband as well. So there is a lot of flexibility there in the deployment. In addition, there is one more spectrum related concept in NR called bandwidth part. Most base stations can utilize the wider bandwidths available in 5G. However, user equipment capabilities can be different for different handsets, and hence it will be more challenging for some UEs to use that larger available bandwidth. For example, some low cost smartphones may struggle to utilize the full bandwidth or the full capacity of the bandwidth, even if a UE is capable of using wide bandwidths, but maybe it do not need to use wide bandwidth continuously. For example, the UE just transferring a very small amount of data, like notification or small messages, etc. So there is no need to use wide bandwidth in such needs. Wide bandwidths also drains more battery, so it is also impacts the battery life of the device. So considering all these requirements, NR introduced bandwidth part. A bandwidth part, or BWP in short, is a subset of contiguous resources block on a carrier. You can see this in the picture. Here you have one single carrier at the top and it has multiple bandwidth parts like BWP1 and BWP2. Like a wider bandwidth part is in blue color and the narrower bandwidth part is in green color. Now here is the important thing that each of these bandwidth part on a carrier, they can both have different numerology. This means they can be completely different in subcarrier spacing, symbol duration and cyclic prefix lengths, etc. There is also a lot of flexibility that how the bandwidth parts can be set up in a carrier as seen in the figure. A UE can be configured with up to 4 bandwidth parts, but only one can be active at any specific one point of time. For example, when a smartphone has a busty data to send, then the network configures that device for a wider bandwidth part. And when there is a very little data to send, then the network will configure that UE for a narrower bandwidth part. And hence, the network resources can be utilized properly and it saves the battery life of the devices as well. I believe you get some insights on spectrum allocations in 5G NR. We discussed about some of the concepts in 5G NR2 like carrier aggregation and bandwidth part, which are important for optimizing the 5G performance and network efficiency. Now, in this session, we will be talking about dual connectivity concept in 5G NR. Dual connectivity is a feature that enhances the performance and the reliability of the modern wireless networks. Consider a scenario where a 4G E node B is providing the main coverage for a user device, and at the same time, the UE can also connect to a nearby 5G G node B coverage. If the UE only connects to the 4G E node B, then it can have the benefit of better coverage, but the data rates would be relatively low. And if the UE only connects to the 5G G node B, then it can enjoy the faster data rates, but at the same time, it may experience weaker coverage or frequent handovers due to more limited coverage of 5G signals, especially on the higher bands. Now, if you look at the protocol stack, then you will notice two types of data barriers. The MCG barrier from the primary node and the SCG barrier from the secondary node. MCG stands for master cell group and SCG refers to the secondary cell group. Another important concept is split barrier. In case of split barrier, one of the node forwards the data plane packets to the another node over to the X2 interface, and later the data is combined at the PDCP layer before it reaches to the core network. The split barriers can be terminated at either the primary node or secondary node. It depends on the network configuration. It is important to note that for split barriers, it is generally preferred and recommended that the primary node and the secondary node are co-located because there would be a significant amount of data transfer needs to be routed over the X2 interface. If you remember, we discussed about the option 3 during the 5G deployment option session. So option 3 refers to the dual connectivity between 5G NR and 4G LTE using a 4G core network. You can see this in the center architecture in this picture here. Now, if the user plane data is split between the MCG and SCG, then it is known as option 3A. If the user plane is handled only through the MCG, this configuration is referred as option 3. And if the user plane data is managed by the SCG, it identifies as option 3X. So you can see in the center architecture for option 3, user plane data is routed from EPC to E node B, and then portion of data is routed to G node B, and then both E node B and G node B sends this user plane data to the UE simultaneously. And later UE will combine these all data received from different nodes. So this is option 3. Now coming to the option 3A in the left architecture. This is option 3A. So here control plane data is handled by E node B, but user plane data is directly routed to the G node B from SCG. Now it is not routed by the E node B. So one stream coming directly from EPC to E node B, and second stream directly coming from EPC to G node B. Then they are sending data to the UE simultaneously over the air. Now coming to the option 3X in the right architecture. So this is similar to the option 3, but here is a small difference. Now first the user plane data is routed from EPC to G node B, and then one stream is transmitted to the UE from this G node B, and second stream is routed to the E node B, and then E node B will transmit that stream towards the UE. Dual connectivity offers multiple benefits to improve network performance and user experience. With dual connectivity, the UE connects to the both nodes at the same time. So it has fast and efficient load balancing across the network. NR coverage from the millimeter wave bands may be inconsistent due to its bad propagation characteristics. So in such scenarios, dual connectivity can enhance the mobility and robustness of the network and can ensure more stable connections even in challenging environments. In addition, dual connectivity can help to accomplish higher data rates and per user throughput because it can use both the radio access technologies at the same time. Now, in this session, we will explore the concept of flexible numerology in 5G. We will understand that why it is important, and we will see that how it works within the network. Let's begin by looking at the LTE frame structure, and then we will compare it with the 5G NR frame structure to understand the differences and improvements. Similar to LTE, the NR frame in 5G is also 10 millisecond long. So this frame length is common for both the technologies. Today, LTE supports carrier bandwidth of up to 20 MHz, and it uses a fixed OFDM numerology with consistent parameters across the network. LTE employs a 15 kHz spacing between OFDM subcarriers, and this is standard across the whole LTE network. LTE frames are divided into two slots. Each slot has zero point 0.5 millisecond, and each slot contains 6 or 7 OFDM symbols. So in LTE, the symbol duration is approximately 66 microseconds, which is same across the all LTE deployments. Now, when designing a new air interface like 5G, it's important to carefully select an appropriate symbol duration to optimize the performance. But before that, let's understand two important concepts that affect symbol duration. These concepts are delay spread and coherence time. Both of them are important concepts in wireless communications. Delay spread refers to the time difference between when the first and last significant signal reflections arrives at the receiver due to multipath propagation. So if you send an impulse in the air, then there is a concept called multipath effect. So when this impulse is transmitted, it takes various paths and reflections to reach at the receiver. And because they are reflecting from different surfaces and follow different paths, this one signal impulse reaches at the receiver in multiple pulses. And because of different paths, they arrive at the receiver with slightly different times. This variation in the arrival times is named as delay spread, which is a key factor in wireless communication. Larger cells usually experience higher delay spreads. So the delay spread is the gap of duration between the first receiving impulse and last receiving pulse. Now let's discuss coherence time. So coherence time refers to the time period during which the characteristics of a communication channel remains relatively constant. It is the duration over which the channel response is stable. means it does not change significantly. Higher frequency bands and faster moving user equipments or UEs typically results in shorter coherence time due to rapid change in the channel conditions. Now the concept is to ensure the reliable communication, the symbol duration should be shorter than the coherence time and significantly longer than the delay spread. And from the 5G spectrum, we've seen that a 5G supports multiple frequency bands, including multimeter bands. Now, 5G is expected to support a wide range of frequency bands and various cell sizes and fast moving user equipment. Now, because of this diversity, a single symbol duration is insufficient to meet all these needs of different scenarios. So, we are needing additional flexibility to select the symbol duration. And to address this, 5G NR introduces flexible numerology. Now, that allows various symbol durations to match the different use cases and network conditions. Like LTE, 5G NR also have a 10 millisecond frame structure, but now it has added more flexibility in the subcarrier spacing. Means unlike LTE, 5G NR supports a range of subcarrier spacing that is from 15 kHz to 240 kHz. So that provides more adaptability for the different scenarios. Although this picture here only shows up to 120 kHz, but please remember that NR can support up to 240 kHz subcarrier spacing for even more flexibility. Each NR subframe is still limited to 14 OFDM symbols, just like we have LTE, but 5G can adjust the subcarrier spacing. So the number of symbols per frame is fixed at 14, but the duration of each slot decreases as the subcarrier spacing increases. So it allows faster data transmission. And hence, larger subcarrier spacing helps in reducing latency as well because it allows data to be transmitted in a shorter slot durations, which is crucial for time sensitive applications. This kind of flexibility brings the better configuration for different type of deployments according to their most suitable properties. For example, outdoor macro cells operating on the lower frequency bands like 700 MHz can use 15 kHz subcarrier spacing, which is better suited for the environments with high multipath interference. Mid-sized indoor deployments can use 30 kHz or 60 kHz subcarrier spacing due to their smaller cell size and the need of efficient spectrum uses. Although millimeter wave deployments, which offers extremely high bandwidths, they require careful selection of subcarrier spacing. So if you use a smaller subcarrier spacing in these high frequency band, then the FFT computation or fast Fourier transform computations can be more complex and challenging. In addition, they also have smaller cell sizes, so a higher subcarrier spacing suits them better. I believe now you have some basic understanding on 5G NR, flexible numerology, and how to use it in network for better performance and for better user experience. This was also one of the major update in 5G NR network compared to the legacy 4G ALT network. Explore two additional features in 5G NR that further contribute to achieving lower latencies. In LTE, the transmission time interval or TTI is the duration of a transmission slot and it is fixed at 1 millisecond. As shown in picture, the shortest delay in the LTE between a downlink data transmission and the corresponding ACK or NAC notification in the uplink is 4 milliseconds. Although this 4 millisecond delay is acceptable for the mobile broadband applications, but it is too long for the ultra reliable low latency communication or URLLC use cases. In 5G NR, this delay can be significantly reduced, which make it more suitable for low latency applications. So 5G NR introduced the concept of self-contained slots. This self-contained slot allows more efficient data transmission, especially in TDD systems or time division duplex systems. This means that within a TDD band, the downlink data, guard period, and the corresponding ACK or NAC notification can all be accommodated within a 500 millisecond slot. Now, depending on the numerology, this entire process can be completed within a single slot. A part of the self-contained slot and flexible subcarrier spacing, 5G NR also introduced another concept of mini slot, which provides even more flexibility in the data transmission. A mini slot is just a shortened version of a regular slot. This is introduced to further reduce the latency by allowing quicker data transmissions. In NR, a mini slot can start at any symbol boundary. So there is no need to wait for the next slot boundary to schedule any data. That is why it reduces the delay. Additionally, the mini slot is not fixed in length. It can contain either 2 or 4 or 7 symbols. However, a standard slot is fixed at 14 symbols. So, mini slots can offer flexibility in slot duration based on the specific needs of the transmission. And this is especially beneficial for the low latency applications. This flexibility in the duration and start time allows low latency devices to transmit data without waiting for the next slot boundary or being constrained by a long slot. And this is effectively minimize the latency. Now let's talk about preemptive scheduling and understand how it works in practice. So in this scenario, the Mac scheduler initially allocates some resources to a mobile broadband UE, which you can see here with the gray color. But then we steal some resources from this pre-scheduled mobile broadband transmissions and reallocate that resource to transmit URLLC data, which is in red color. This happens to ensure that the URLLC low latency data gets the priority. This approach is known as preemptive scheduling, where URLLC data can override the pre-scheduled transmissions to meet its strict latency requirements. Now, if we are doing this, then we need to inform the UE as well that some of the scheduled slots are now used for other services. And for this purpose, a preemption indicator is sent, and UE get notified that some of its resources have been reallocated for URLLC data transmissions. These different level of flexibility are helping 5G NR to achieve lower latency, as URLLC data can be scheduled with a lot of flexibility in slot duration and slot time. Typically, the UE monitors the downlink control information channel or DCI channel to know when it needs to receive data. The UE monitors the channel at the beginning of each slot and then goes into the sleep mode for the rest of the slot duration to save the battery power. However, for the low latency devices that uses mini slots and the data can be scheduled at any time and at any slot, so we have a trade-off here because low latency devices has to constantly monitor the DCI channel and hence they cannot sleep between the slot boundaries and this increases the power consumption. Therefore, it's essential to understand the trade-off between achieving a low latency and maintaining the power efficiency. In summary, mini slots and preemptive schedulings are the important design innovations in 5G NR to serve the ultra reliable and low latency use cases, and they significantly contribute in achieving this low latency requirements for the next generation applications. Now, in this session, we will be discussing 5G NR scheduling. In 5G NR, scheduling options are specifically designed to meet the wide needs of various use cases, from mobile broadband to low latency applications. Let's start from the downlink scheduling options. So we have two scheduling options for downlink data transmission. One is for mobile broadband and another is for low latency communication. For mobile broadband data, whenever there is a downlink data to send, the G node B informs the UE through the downlink control information and then sends the data. However, this approach may be too slow for the low latency data transmissions. So low latency transmissions occurs periodically. So instead of DCI, a RRC message is used to define this periodicity. And at that period, the UE can receive the data without any further notifications. And this technique is called semi-persistent scheduling, SPS or SPI. And it is important for maintaining that low latency in periodic data transmissions. Now let's look at the uplink scheduling. So this is for broadband data transfer in uplink. When there is a uplink data to send, then first UE will transmit the scheduling request to the base station. Then the base station responds to that request by sending a scheduling grant, and that passes through a PDCCH or physical downlink control channel. Then the UE will respond to this grant by transmitting its data on the PUSCH or physical uplink shared channel. This method is called dynamic scheduling So this whole process can have higher latency because all the uplink transmissions are orthogonal. This means that two UEs cannot transmit their data simultaneously on the same resources. This is needed so that uplink transmission do not interfere with each other, and hence each UE is assigned by a unique resources. And because of this, UE needs to rely on the base station to assign the resources to them, and that leads to the increased latency. This method of requesting and receiving a grant works well for the broadband data, where latency is not that much critical. But for the low latency requirement, this request and grant process is little bit long, and it takes several milliseconds from the initial scheduling request to the final data transmission. And hence, for the low latency use cases, 5G NR introduced more efficient technique called as configured grant or configured scheduling. Now, configured grant comes in two variants, and each one is designed for different type of uplink data needs. Type 1 is ideal for the UEs which have periodic data to send. In such use cases, the network can grant the periodic uplink resources to the UE. So there is no need to request a grant every time. Whenever the UE has data to send, it can immediately transmit that using these pre-configured resources without the need of dynamic uplink grant. This approach significantly reduces the uplink latency and make it crucial for the applications with stringent latency requirements. But what if the data is not periodic? In such cases, periodic resource allocations could lead to an inefficiencies and it will waste the network resources. So this brings us to the type 2 configured grant. With type 2, uplink resources are still granted periodically, just like we discussed in type 1. But now in this type 2, PDCCH will be used as dynamically activate or deactivate these grants based on their needs. So depending on the packet arrival time, the PDCCH can be used to adjust the fraction of grants that are actively used. Although this approach increases the signaling overhead on the PDCCH, but it enhances the efficiency and minimizes the resource wastage. It was just a brief, as this series is focused to introduce different concepts of 5G NR. We've seen how different scheduling processes are ideal for different needs and different use cases, and what should be used for mobile broadband applications and what should be used for low latency applications. Now, let's understand the concept of quality of service, QoS. We will understand its importance and the basic principles of QoS. Well, QoS concept is not new. It is already being used in 4G LTE, but we will know that how it is evolved to meet the demands of 5G networks. Before understanding 5G QoS, we need to understand what is QoS or quality of service. In short, quality of service offers the ability to manage different type of traffic, which has different network demands and different requirements from the network. And it ensures that each type of traffic gets the appropriate level of resources and services. We will be understanding this in details in some time. So a network can handle different type of traffic, which have different requirements. For example, a voice call should be treated differently than a data transfer service. Same for a video streaming service. All of these use cases requires different levels of service to function properly. Sometimes even a single user device may need multiple connections simultaneously, and each for different type of traffic, such as voice, video, and data services. For example, when a user device or a UE makes a voice call, it needs a continuous delay sensitive stream for data, but that require relatively low data rate. But for some heavy file transfer, UE requires a different type of connection, which can handle bursty data traffic. So this type of service is less sensitive to delays, but that should offer higher data rates, right? So this brings the need of quality of service, where different type of services can operate efficiently and meet user expectations. A QoS parameter defines some critical characteristics or parameters. For example, what is permissible packet delay, what is acceptable packet error loss, and other metrics that determine the quality of connection. So, how does the network manages and prioritize the traffic from these different type of services to maintain the required QoS? One of the fundamental requirements for communication in any network is to obtain an IP address to a UE. One UE can be assigned one or more IP addresses depending on the services it needs to access. In 2G and 3G networks, obtaining an IP address was referred as establishing a PDP context, where PDP stands for Packet Data Protocol. In 4G, this operation is referred as establishing a PDN connection, and it is managed using the concept of barriers. A barrier is simply a dedicated transmission path through the network with some defined capacity and latency and packet loss kind of characteristics. You can assume this barrier as a concatenation of various tunnels in the radio access network and the core network. So this complete barrier links the UE to the packet data network. Now, if there are multiple barriers established, then each barrier is associated with some specific QoS level, which ensures that the service requirements are met. In 4G, a default barrier is automatically established to a default packet gateway when the UE is powered on and has successful authentication. Every PDN connection in 4G has at least one default barrier to handle the basic traffic. In addition, dedicated barriers can be set up whenever they are needed, such as when there is a need for voice call or need of data transfer or online gaming, etc. In 4G, QCI or quality of service class identifier is the parameter which is used to define the specific QoS characteristics for a connection. Depending on the QCI values, there are two kinds of barriers. The first one is called GBR barrier or guaranteed bitrate barrier, and the another one is non-GBR barriers or non-guaranteed bitrate barrier. Now this table is the relationship between the QCI value and its corresponding barrier type and packet delays and packet error rate. In the radio access network, scheduler looks for this QCI identifier to set the right priorities to achieve the QoS parameters like delay and error loss, etc. for all the services it is serving. Similarly, in the core network, routers and switches also use QCI to manage the traffic priorities and maintain the QoS. In 5G, this process of obtaining an IP address is now referred as establishing a PDU session, where PDU stands for Protocol Data Unit. One single UE can also have one or more PDU sessions, depending on its needs. In 5G, the concept of barrier now has been replaced by QoS flows, although they serve a similar purpose. So each PDU session in 5G can have one or more QoS flows, and each PDU session corresponds to the different quality of service performances. Just like barriers in 4G, QoS flows in 5G also have a series of tunnels throughout the network, which are configured to meet the specific service requirements. The difference in 5G is that there is only one entry tunnel per PDU session. In 5G, different radio barriers corresponds to different quality of service performances, and all are mapped to the same N3 tunnel in the given PDU session. In 5G, the QCI parameter is replaced by 5QI or 5G quality of service identifier, although their concept is same. Now, based on the 5QI value, 5G networks have three kind of barriers. So 5G has one extra QoS compared to the 4G QCI. So these types are guaranteed bitrate or GBR, non-guaranteed bitrate or non-GBR, and the third category is known as delay critical GBR. This is specifically designed for ultra reliable low latency communication or URLLC use cases. We have explored the principles behind the QoS in 4G and 5G. We understand that how the networks manages different type of traffic to ensure the appropriate level of services for various applications. Now we will see that how 5G quality of services meet the requirements of massive machine type communication or mMTC use cases in 5G. Massive machine type communications or mMTC is one of the segments from three major use cases of 5G. It refers to connect a large number of devices like up to 50,000 devices per cell. These devices are low cost devices and they are just designed to transmit very small amount of data. These devices needs longer battery life, like up to 10 years on just a couple of batteries. And they require strong coverage, even in the challenging locations like buildings and basements, because these devices can be placed at any point. We are needing such a low cost devices which also have longer battery life with extended coverage, because these devices are supposed to send or receive very small amount of data, just like a few hundred bytes per day. Currently, the demand of mMTC devices is met by two technologies, which was evolved from native 4G LTE network. And these are eMTC or CAT M1 and narrowband IoT CAT NB1. The mMTC features based on 5G NR are still evolving. So, for the time being, these two technologies mainly cater the demand of mMTC use cases. Now, let's look at the key principle behind eMTC and narrowband IoT. The first goal in mMTC is to design a low complexity and a low cost device. Devices that supported LTE Release 8 features were called Category 4 devices or Cat 4 devices. These devices can achieve downlink speed of 150 Mbps, and they are able to use 64 QAM modulation for downlink. And they also support 16 QAM modulation in uplink. They support 2 by 2 MIMO, and they can utilize the bandwidth up to 20 MHz. And the transmit power is up to 23 dBm. For mMTC, we need devices that are simpler and cheaper. So, in later 3GPP releases, these features were scaled down to meet the mMTC requirements. In release 13, two specific technologies were introduced: eMTC or CAT M1 and narrowband IoT or CAT NB1. Because mMTC devices sends very little data, so their peak data rates were reduced to under 1 Mbps for eMTC and a few hundred kilobits per second for narrowband IoT. Also, the modulation schemes were limited to 16 QM and QPSK. And because of these reductions, the complexity of the devices gets reduced and the cost is also significantly reduced. Additionally, there is no support of MIMO in these devices. These are only using one single transmit antenna and one receive antenna. And the bandwidth is also limited to 1 MHz for eMTC and 180 kHz for narrowband IoT. And because of these narrow bandwidth, the receivers and transmitters become simple in design and they also consume less power. Additionally, the transmit power of these devices can optionally be reduced to 20 dBm, which ultimately helps in lowering the cost, complexity, and extend the battery life. Full duplex communication is also optional in eMTC technologies that also simplifies the design. The main difference between these two technologies is that CAT M1 mainly caters to devices that need significantly higher data rates or support for voice traffic as well, while narrowband IoT is useful for the devices which require even lower data needs. By simplifying these features, the complexity of the devices is reduced nearly 15 to 20% of a typical LTE mobile broadband chipset. So, this approach allowed manufacturers to develop low cost and low complexity devices, very specific to the mMTC use cases. Now, the next question is how we can achieve long battery life for these devices. mMTC devices targeted to support up to 10 years of battery life with just couple of batteries. So, in addition to have a low complexity modem, we have two more concepts to help improving the battery life. Let's look at them. Usually, when a device sends some data, it normally enters into the connected mode to transmit the information, and that required power. And once the data transfer is completed, then it moves into the ideal mode, and it also switch off its receivers to save power. But the problem is, if device is in sleep mode, then how the device will know that there is some data for it to receive? So it need to check paging information. But instead of continuously looking for the paging information, the device only check the paging information at some time interval. And for rest of the time, it goes into the ideal mode. This idea is called DRX or discontinuous reception, where the device check for the paging information at some time interval. In LTE, this DRX cycle is limited to 2.56 seconds. But because mMTC devices handles infrequent data, so they can even use longer DRX cycles to save power. This extended cycle is called EDRX or extended DRX. In eMTC, EDRX can be up to 43 minutes. And in narrowband IoT, it can be up to 3 hours. With this extended DRX concept, devices check for their paging less frequently, which also help in saving the power. But what if the data is even less frequent? What if there is no data to check even for more than 3 hours? In such cases, the device enters into the power saving mode or PSM, which is the second key feature. In PCM mode, the device enters into the power saving mode and it only consumes very least amount of power. In this power saving state, the mobile is registered in the network, but that does not monitor any paging information, and hence it becomes unreachable from the network point of view. Now, when the device wakes up after the agreed period, then it can send and receive the data again with the network. You will be wondered, but power saving mode can be used for up to 413 days, which is a significant amount of time. So together, EDRX and PSM techniques are helping to extend the battery life of mMTC devices. EDRX handles the interval up to 3 hours, and if the application can wait for the longer period, then the power saving mode can be used. Okay, now let's talk that how we can achieve extended coverage. eMTC offers up to 10 dB more coverage compared to the GPRS and narrowband IoT, and it offers up to 20 dB more coverage than the GPRS. In both technologies, the key principle is to extend the transmission time by repeating the same packet multiple times. By repeating the same packet multiple times, receiver can accumulate more energy from each packet. This method can be used to extend the coverage by up to 20 dB. Means devices which are far from the base station or if they are deep inside the building, they can still have possibilities to receive the signal. Narrowband IoT and eMTC can use up to 2048 repetitions in downlink and 128 repetitions in uplink data channels. The number of repetitions is determined by the device coverage. If it is in a bad coverage, then the transmissions will be more. If it is in a good radio condition, then the transmissions will be less. And because of these repetitions, eMTC can achieve up to 10 dB better coverage than the GPRS and 15 dB better coverage over the LTE. While narrowband IoT can have up to 20 dB better coverage than the GPRS and 25 dB better coverage over LTE. In addition to this, there is a second aspect. Control channels can also be limiting factor in coverage. So the power levels of the control channels can also be increased to improve the coverage. But that need to be done very carefully and should only apply to those control channels which are the limiting factors of the coverage. So these are the two main techniques which can be used to improve coverage for mMTC devices. Now let's quickly see that how these technologies can be deployed on existing LTE networks. So eMTC can be directly multiplexed into the existing LTE carrier. You can see this in this picture here. For example, if there is a 20 MHz LTE carrier, a 1.4 MHz portion can be allocated for eMTC access. Even this chunk of spectrum can be time shared between eMTC and non-eMTC devices, depending on the traffic and uses. The rest of the spectrum can be used to serve the regular LTE traffic, like as usual. Similar deployments can also be applied to NR spectrum, as you can see here. However, narrowband IoT supports even more flexible deployment. First, just like eMTC, it can be multiplexed into the LTE carrier. Additionally, it can also be deployed standalone in the guard band between two carriers. It can also be deployed as a completely standalone system with a dedicated spectrum. Narrowband IoT supports all these three types of deployment options. Well, regardless of choosing options, both of these technologies can seamlessly integrate into the existing LTE networks. They can provide mMTC-based services, and depending on the traffic, it can do time sharing to share the load between LTE broadband and massive machine type communication use cases. Now let's explore the 5G cell and understand how the concept of a cell has evolved in 5G technology. A cell is a geographical area over which a certain base station provides the coverage for the telecommunication network. At the very beginning of wireless communication, omnidirectional antennas were used, and they were represented by a hexagon with a base station in the center. However, later we started using cell sectors to increase the cell capacity and coverage. Now these three sectors are called individual cells, and these corresponding to the one base station. At the bottom picture, this is a better representation where a base station is placed at the corner of the hexagon, and now it has three hexagons. Each hexagon represents individual cell. In 5G, we have a new concept called beamforming. So the concept of a cell is further evolved for this purpose. We will see that in some time. Now let's talk about cell search. So when a UE or device is turned on or when it moves into a new cell, then it has to synchronize with the serving cell and it has to obtain basic information about the cell like system bandwidth, etc. This is the initial step, and this synchronization must happen before any transmission or reception of data to the device. For this purpose of cell search, in LTE, each cell transmits two types of synchronization signals. These are the primary synchronization signal or PSS and the secondary synchronization signal or SSS. The UE listens to these signals to synchronize with the cell and obtain the physical cell ID. After synchronization, the next step is to acquire the cell system information. This system information is continuously broadcasted by the network, and this is essential for the UEs to access and operate correctly within the specific cell. The system information includes downlink and uplink bandwidth data. It also includes TDD configurations and parameters for random access. This system information is delivered by two different mechanisms and through two different channels. First is Master Information Block or MIB. MIB is delivered by the broadcast channel. And second is System Information Block or SIB. System information blocks are delivered through the downlink shared channel. Note that there is only one MIB type message, but there are several SIB type messages like SIB1, SIB2, SIB3 and up to SIB9. When we talk about NR, we also have primary synchronization signal PSS, secondary synchronization signal SSS and master information block MIB, and we also have system information block SIB. However, to reduce the amount of broadcasted information, network only broadcasts very few information in broadcasting. So instead broadcasting all of the informations continuously, only a subset of this information is broadcasted. This is known as cell specific information. This is the minimum amount of information that required for random access. The rest of the information is sent directly whenever they are needed. In NR, this similar concept is called SS block, which includes the primary synchronization signal PSS, secondary synchronization signal SSS, and master information block MIB. The main difference in NR is that multiple transmissions and reception points can transmit the same SS block, and hence they act together like one cell. Let's understand this with one example. So consider we have one base station that supports beamforming in 5G NR, and a small cell that does not support beamforming obviously, and one another base station that also using beamforming. Now if all of them are transmitting the same SSB, then they will act like one single cell. So when a UE moves from one cell area to the another cell area, then the serving beam can switch from one beam to another beam, regardless they are a part of a single base station or different base stations. This allows flexible deployment options and reduces control signaling overhead, as mobility related signaling are reduced now towards the core network. Therefore, different transmissions and reception points are collectively treated as a single cell, as long as they are transmitting the same SSB. SSB can be either broadcasted or it can be beamformed if there is a coverage constraint. Now let's talk about RRC. We will talk about different RRC states in 4G and 5G, and we will understand how the RRC states works in 5G, and we will also see how the transactions happens between different RRC states. The connection of a UE to a 5G network is handled through a state machine, and the transactions happens between different RRC states. Compared to 5G, in LTE we only had two RRC states, RRC idle and RRC connected. When the UE is actively sending or receiving any data, then it is in the RRC connected state. And when the UE is not actively transferring data, then it goes to the RRC idle state to save battery. The transactions between these two states requires defined process, like establishing a new connection and releasing a connection, etc. And that also involves the core network. These processes are called RRC connect when network set up a new RRC connection, and RRC release when network releasing the existing RRC connection. However, there was a problem in this approach from 4G because you frequently switch between these two states. Even for a small amount of data transfer, such as a simple notification or a small message, it requires established connection, and that required signaling every time for the RRC connection process. To improve this situation, 5G introduced a new state called RRC inactive. The RRC inactive state allows the UE to save power during the sleep mode, but this state do not release the RRC connections completely. So we have a new state and two new transactions in 5G NR. To move from RRC inactive state and RRC connected state, we use RRC resume procedure. And to move from RRC connected state to RRC inactive state, we use RRC suspend procedure. And for all these switchings between RRC inactive state and RRC connected state, we do not need to set up a new connection or releasing an old connection, because these transactions handled by UE and radio access network. So the core network do not involve here. When a connection is established and the UE enters to the RRC connected state, it also sets up the radio configuration and security parameters for the connection. Now when UE moves from RRC connected state to RRC inactive state, then this is the suspend procedure. And during the suspend procedure, UE and radio access network keeps those radio configuration and security parameters. And then when the UE needs to connect to the network again, for example, when there is some uplink data to transfer, then the UE starts the resume procedure. Resume procedure restores the saved radio configuration and the security configuration data and resume the connection very quickly. Hence, we do not need extensive signaling with the core network. Now, because the resume procedure is faster than setting up a new connection, so it also helps to reduce the latency. In most of the cases, when the UE comes out from the power saving mode, it always tries to connect to the same cell site from which it is previously connected. But if the UE resumes in a cell that is served by a different cell site, then the target node will retrieve the UE configuration from the previous cell site based on the UE identifier. So in 5G, the RRC idle state is mainly used as an initial state or as a fallback if a connection fails. The resume procedure significantly reduces the number of RRC messages between UE and radio access network. In LTE, when we go from RRC idle state to RRC connected state, it took 7 messages, as you see in this picture here. So it takes longer time to connect, means it has more delay. But with this new RRC state, when we move from RRC inactive state to RRC connected state, now it just takes 3 messages. And we have RRC connection established very quickly compared to the legacy LTE network. So this reduction in RRC signaling significantly reduces the latency. And as a result, our network becomes more responsive. And this supports more end user services, which demands better response time from the network. It also reduces the power consumption for the devices such as battery powered sensors that only sends a small amount of infrequent data, generally less than 100 bytes of data. We talked about RRC states in 4G and 5G, and we talked about the state machines for the transactions happening between these RRC states. We also discussed new RRC state in 5G, which is RRC inactive, and we learned how it can help to improve latency and overall network responsiveness, and how it reduces the signaling overhead between radio access network and core network. Now let's have some overview on 5G core network. Well, we all know that when LTE was first introduced, it has focused on providing two main services. First is voice call and second is mobile broadband. LTE uses two types of connections to support these two services. Number one is guaranteed bitrate for voice, and number two is non-guaranteed bitrate for broadband services. But 5G is designed to handle a wide range of services, and each service has different needs and performance requirements, means different quality of services. For example, some of these services are massive machine type communication or mMTC, which send very small amount of data after some specific period. We have EMBB services or enhanced mobile broadband service, which handles large amount of data transfer. Next, we have ultra reliable low latency service or URLLC service. These services are time sensitive and hence they require a better latency from network. So you can say that 5G is one single network, but that has to support many different type of services. To handle all these different type of services, 5G network has to be very flexible. However, as a general phenomena, more flexibility comes with more complexity. So we are needing more automation and programmability in 5G network compared to the 4G network so that we can reduce some of the complexity in the 5G network. So for all these purposes and to make 5G more powerful and more flexible, we developed some of the new concepts like network slicing, service-based architecture, network virtualization, etc. It is also important to note that if operators only provide basic connectivity, then their business growth is expected to be just 1.5% per year. But if telecom operators also becomes service enablers or even service providers, then they can grow their businesses much more. And based on the studies, their revenue can grow nearly 13.6%, as you can see in the right side. And this is actually a very good growth compared to the legacy services. Here we have a detailed view of a market size for operators when they are acting as a connectivity provider or if they are acting as a service enablers or even as a service provider. So as you can see that there is more revenue potential when operators act as a service provider. To understand this, first we need to understand the role of connectivity provider, service enablers and service providers. So in very short, a connectivity provider simply offers the basic telecom infrastructure and internet connection. Next is service enabler, when the operators allows their network capabilities to the other companies so that they can build their own application on top of their network infrastructure. And third is service provider, when the operator builds their own services on top of their network capabilities and provides those services to the end user. Let's look at some simple examples. Let's assume that AT&T launches its own streaming services just like Netflix. In this case, AT&T will act as a service provider and the services would be video streaming and on-demand TV shows. On the other hand, operator can also offer their network storage capabilities to a company like Netflix. This means operator is allowing Netflix to use their data centers to provide better viewing experience on 5G devices. Netflix can also build their application on those data centers. In such cases, operator will act as a service enabler and it is allowing Netflix to utilize their network capabilities and storage capabilities. The third possibility is that the operator can just provide the internet service and the third party company offers a streaming network and streaming services and they will store their content outside the operator network. In this case, the operator role is just like a connectivity provider. If we consider all these different type of roles and if operators also play an active role as a service enabler or even as a service provider, then there is a strong possibility for operators to gain a bigger market share from the 5G potential. And as an operator to play these different type of roles and to become service enabler or even service provider, operators actually need to implement new concepts and technology like network slicing, service-based architecture, network virtualization, etc., which we will be talking about. We discussed how operator can gain a bigger market share from the 5G potential. Now let's talk about different elements of 5G core network and let's say how they are different from the 4G core network. Here we will know that what are the new elements that are added in 5G core and how the responsibilities are divided into new 5G core elements. Okay, so what are the new key elements in 5G core network? Well, before moving to the 5G core, let's quickly see 4G core architecture first. The 4G EPC core or Evolved Packet Core is relatively simple. It includes the Mobility Management Entity (MME), which handles mobility management related tasks and session management related tasks and UE authentication. The Serving Gateway or SGW is responsible for transferring user data between the 4G radio access network (RAN) and Packet Gateway Network or PGW. The packet gateway takes the user data from the serving gateway and sends it to the external network, for example, internet. The packet gateway also assigns IP address to the UE device and ensures that the quality of service rules are followed. HSS or Home Subscriber Server stores the customer profile and creates the authentication data. Then MME uses this data to verify users. PCRF or Policy and Charging Rule functions provides the quality of service information to the packet gateway for different type of traffic. It also has charging rules, flow control rules and traffic priority, etc. so that it can correctly charge the device for using the services. Now let's look at the 5G core network architecture. But before understanding that, I want to cover one important concept in 5G. Well, one of the key idea in 5G technology is separating the control plane functions and user plane functions. This is known as control plane and user plane separations or CUPs. We talked about this earlier. In 4G, the serving gateway and packet gateway combinedly handles different tasks like assigning IP address to the UE, charging the UE, enforcing quality of services, etc. And they provide a mobility anchor, packet routing, etc. In 5G, these control plane functions and user plane functions are now separated. So the user plane functions from the serving gateway and the packet gateway are now combined into one single entity. And this is called user plane function or UPF in 5G. And the control plane tasks from the serving gateway and packet gateway along with the session management are now handled by session management functions or SMF in 5G. Mobility management is now managed by access and mobility management function or AMF in 5G. Authentication is handled separately by authentication server function or AUSF in 5G core. And the MME functions are now distributed between AMF, SMF and AUSF in 5G core network. The policy control functions or PCRF in 4G EPC core is now evolved to the policy control function or PCF in 5G core. In 4G EPC core, HSS was managing the subscriber profiles and was creating the authentication data for the MME. But in 5G core, subscriber profiles and the creation of authentication data are handled by Unified Data Management or UDM. So this is how the 5G core network functions are divided compared to the 4G core network. We learned what are the new elements that are added in the 5G core and how the responsibilities are divided into the 5G core elements. Now we will discuss network slicing. So what is network slicing? Well, to understand this, we need to understand current network system first. So today's networks looks like this in the left. We have a basic telecom network system, and on top of this network, we offer services like voice calls and mobile broadband. Now, different type of use cases such as social media or video streaming, downloads, uploads, playing video games, etc. All of such use cases are using these services from the operator. So you can feel that currently most of the use cases are mainly depend on mobile broadband services. However, in 5G, there is a completely new category of use cases. These new use cases are like massive machine type communication or mMTC and ultra reliable low latency communication or URLLC services, and of course enhanced mobile broadband services use cases or EMBB services. Now, these all use cases have different network demands and hence all of them require very specific network characteristics. This means our network should be capable to handle those different network demands and performances. To simplify it, just assume that you have one individual network system for each use cases based on their network demands, like you see in the right section. So in 5G, we have one physical network, but we can create multiple logical networks on top of it. These logical networks are known as network slices. And this concept of creating multiple virtual networks on a common and shared physical infrastructure is called network slicing. And each of these network slices can be configured independently, specifically for their use cases. This means you can specify the network demands and their characteristics for each use cases like latency, capacity, coverage, etc. For example, if any device wanted to use massive machine type communication, then it will connect through that specific network slice. And that slice was already optimized for infrequent data transfers, and that also supports capabilities for longer battery life, which is needed for mMTC based services. One slice can be dedicated for mobile broadband services, which will only handle heavy data transfer or high data rates. And there will be one another slice which is focused for low latency communication, like for self-driving cars and robotic surgeries kind of applications. Even based on the requirement, one single UE can also connect to multiple slices at the same time. For example, a self-driving car needs low latency for communication, but it does not need high data rates, right? However, at the same time, some streaming services also getting accessed from the same vehicle. And now that device also need higher data rates for streaming services. And this streaming services is not heavily depend on the latency requirement, but this needed high data rates. So by using network slicing, we can meet both of these requirements on the same common physical network because now they can be served from two different virtual network slices. Each slice here are completely isolated and traffic on one slice cannot interfere with the traffic on the other slice. Means both of our requirements will be fulfilled because device is accessing two network slices from the network for each separate requirements. On a positive note, this concept also supports new technology upgrades as new requirements or new technology can be deployed in different slices in the network and that will not affect other existing network slices. Network slicing also help in the better security because if some cyber attack happens on one slice, then only that slice will be affected and there is very less possibility that it is spread to the other network slices because these network slices are isolated with each other. Now let's see how these network slices are managed. First, in the core network, there is a specific function for this called as NSSF or Network Slice Selection Function. This NSSF maintains a list of network slice instances defined by the operators, and it also maintains their resource requirements, which is also defined by the operator. A UE may be configured with a list of subscribed network slices, and it can request to get the access to a specific network slice during the registration procedure. Now, the Access and Mobility Management function or AMF will authorize a network slice based on the user subscription data from the UDM or by a query to the NSSF. For example, if a car requests access to the slice for self-driving car, then the NSSF and UDM will work together to authorize it. We learned how the network slicing allows multiple logical networks to run on a single physical network and how each slice can be configured independently to achieve specific network requirements for specific use cases. We also seen how this whole process works in very brief. Now let's talk about 5G service-based architecture. So what is this service-based architecture and how it relates to 5G? Let's understand this by understanding the traditional software development process first, which is often called monolithic architecture. So what is this monolithic architecture? In monolithic architecture, all the software components are combined together into a single package, and everything is delivered and hosted at one single unit. This means that if you need to update one part of your system, then you have to integrate it with other components and rebuild the entire application and then replace the older version with the newer bundle. Well, the problem with this approach is that the updation process is very slow and it is complex too because everything is tightly connected with each other. If one component fails, then it may break the entire system. And that is the reason that monolithic systems are not very flexible. And because all of these parts are interconnected and they are tightly coupled with each other, they are bound to use compatible technologies. And to update just one part, you have to check the compatibility with the entire system. Then only you can rebuild your system to function it correctly. So this type of systems are not easy to scale, and they are also slow down the development time for any new feature. For example, consider that you're building an e-commerce website. And if you build all the features like user management, order processing, inventory management, and user interfaces as one big application, then this is monolithic architecture. Well, today modern applications using a different approach, and this is service oriented architecture or service based architecture, SBA. In service based architecture, the software or the product is broken down into small and individual features, and these independent services or features communicates with each other. Each service can register itself and interact with the other services whenever it is needed. Now, by using this approach, developers can try, mix, and match services from different vendors and technologies. And they can create a single application by using these third party APIs, features, or individual functions. This gives more flexibility to the developers, and now they can develop new features easily and that too in less time. They can interconnect different services and components without needing to create a new interface. Consider the same example of e-commerce website. In this example, now you can break the application into separate services and each service is handling a specific function. Like one function is for order management, another function is for user accounts, one function for inventory, and one function is for payment, etc. And each service will communicate with each other. You can even buy a service from a third party company. For example, for your product, you do not want to build your whole payment gateway system. Then there are companies who are specialized in the payment handling. You can use their functions in your product for payment handling purposes. There is another company who is specialized in the database management. So you can use their services for big database handling for your product. So you can consider the options which is best suits for your requirements, or you can choose best in class services from the top vendors or budget friendly solutions, or whatever which is best fit for your demands. And that will also speed up your whole development cycle, and your time to market will also reduced. Another benefit is independency. For example, suppose by some reason one service fails for your products. Let's consider your payment gateway is broken. Now, if your design is using service based architecture, then it will only impact the payment processing part. The rest of the functionalities and your application can still work like normal. Like user can still continue browsing the items and even they can add the items into their cart. The only thing that will not work is the payment part. Means they will not be able to complete the payment. Of course, this is a major problem. But the point is that your whole application is not down. It is just one function that is stuck. Now think what if just because of this failure of one function or incompatibility with one function, your whole application become useless. Like it is crashing or not operating properly, etc. So this will be a nightmare, right? So in short, in service-based architecture, even if one or two part of your system goes down, you are still able to use your application. In service-based architecture, each function can be developed or deployed or can be scaled independently as long as they are reachable over the web-based interface. In addition, the development is much easier by using APIs and web-based technologies. Developers are also flexible to use libraries or different development tools, code generators, and many other components which are broadly available in the web. So this wide support helps to speed up the initial development and regular development cycles. And of course, it reduces cost. Many developers are already familiar with service-based architecture, so finding the peoples with the right skill set is also easier. Now, the 5G core network also supports service-based architecture. In addition to the traditional point-to-point architecture, 3GPP also define a service-based model for the 5G core network. In the traditional point-to-point architecture, if operator want to add any new network element or new network instances, then it is difficult to add. And this is also more complex because in such requirements, operators may need to reconfigure all the connected interfaces, which can be time consuming. Let's look at the example. In this example, we have this application block. This is labeled as AF. We want to build this application for our system. This is the additional application that we want to build and we want to integrate it with our existing core network. Let's say we are building an analytic function in this application. So for this, we need to specify the interfaces and reconfigure the interfaces for all the connected functions from which the analytic services has to connect. And this is really challenging. Now let's look at the service-based architecture of the core network. Some of the interfaces you see here are protocol-based interfaces, such as N1 using the protocol NGAP and GAP. The interfaces which are specified with the small circles are service-based interfaces. Now it is important that protocol-based interfaces must comply with the 3GPP standards. This service-based interface gives additional layer of flexibility and hence we can develop more innovative functions for control plane applications. For example, this analytic functions which we are talking about. This can interact with all the necessary nodes through a service-based interface and this will allows you to connect the new components with the existing interfaces. In summary, service-based architecture can help in easy development of functions and in updation or upgradation as well. Operators and vendors will be flexible to develop more innovative features which are crucial for evolving needs of 5G network. Now let's talk about virtualization and understand what is NFV, network function virtualization. Because now we have some basic understanding of cloud computing and virtualization, so we can move forward to explore how these technologies can help in telcos and networking. So let's start. Okay, so first understand what is NFV or network function virtualization. Network function virtualization is the technology that transforms that how the network services are deployed by using softwares instead of specialized hardware. Traditionally, network equipment comes with purpose-built hardware. For example, components like mobility management entity or MME and firewalls, etc. They all are tightly coupled with their hardware. These network functions always come with their own specific hardware, means each function has its own physical device. So upgrades and maintenance are challenging on them. The another challenge with those dedicated hardware is that any provisioning, maintenance and decommissioning are labor intensive as they require physical handling of each device. Now with the advancements in virtualization, we can now replace these specialized and property-based hardware devices into software-based solutions, and they can run on general purpose hardware or servers. Network function virtualization or NFV is the process of separating network functions from their dedicated hardware. And after that, they can run as a software on standard hardware or COTS hardware. So the network functions like CDNs and firewalls, etc. Traditionally, they run on the proprietary hardware, but now they can operate on standard data centers. As you see in this diagram, in the left, we have traditional hardware coupled network functions, and in the right, we see that all these functions are decoupled and now deployed on the general purpose hardware. The software-based implementation of network functions such as virtual MME or virtual firewalls, etc. are known as virtualized network functions or VNFs. In 5G networks, all of these core network functions are designed to operate as VNFs. So they can deploy it with the more flexibility and they are easily scalable based on their demand. This includes critical functions like session management function or SMF, authentication server function or AUSF, unified data management or UDM, and all other components mentioned here. When these VNF are deployed using Dockers and containers instead of traditional virtual machines, then they are referred as cloud native implementation. And these cloud native systems are even more efficient and they are more scalable. Now, before going further, Let's understand some background on cloud computing and virtualization. So there are two key technologies that are continuously evolving to manage IT resources. We will understand them with one simple example. Let's say that you need to set up an email server for a company with 500 employees. And we know that load on those servers will not be consistent all of the time, right? Like during the weekdays and in working hours, email traffic will be high. But at the night, it will be very less utilized. Due to this variation in workload, it is difficult to optimize server resources. You can either invest in a server that can handle even more capacity than your peak email traffic, but this approach is not very efficient, as most of your resources will remain unused during non working hours and weekends, so they may not justify your investment. And if you choose a server with a lesser capacity, then of course it will not be able to handle peak load traffic, and there will be unused email requests at the time, and there will be potential downtime during those busy hours. Now you can say that what if we match the server to the peak load? Well, you will still face inefficiencies. And another problem is that your peak load can also change over the time as your company grows or shrinks. So that will require adjustments all of that time. Typically, such personal servers are generally underutilized in most of the cases. Even real-world estimate shows that the average utilization is around 5% to 20%. And this type of approach are not very efficient to deploy or manage. Additionally, if your server hardware fails, then the entire email system can go down, which can affect your company communication and productivity. Cloud computing offers a solution to these challenges by providing flexible and scalable resources that can adapt to your needs. So let's understand what exactly is cloud computing. In simple terms, cloud computing is the on-demand availability of computer system resources. For example, computer storage, computing power, networking, etc. And all this flexibility comes with very less human intervention or even no user management to the physical hardware. For example, in our email server, what if that company prefer to have a subscription to an email service like Gmail Enterprise is offering, which provides the necessary resources on demand. This way, that company gets the access to the computing resources as per their requirements, and they do not need to worry about underutilization issue and overcapacity problem. For example, if your email inbox are full, then you can easily purchase more storage space with just few clicks, or even you can automate that with the cloud services. Or if your company expands and you need more email accounts, then you can quickly add more email accounts to accommodate new employees. This approach ensures that you only use the resources that are needed for your requirements and only pay for those resources. So it eliminates both the challenges of underutilization and overutilization of resources. And this is a cost-effective solution as well. Secondly, you do not need to manage hardware by your own. And you do not need to worry about hardware failures or system failures. And even you do not need to invest in the new servers and storage. The cloud provider or the service provider will handle all of these things for you. The cloud provider such as Google, AWS, etc. share its vast computing resources among many users like you. And hence they can avoid or minimize their resource wastage in much better way than an individual company. And it also reduces their cost as well. In a traditional server-based system, you start with the physical hardware as a foundation. Then an operating system is installed on top of this hardware. Finally, you have one or more applications that are running on the operating system. However, in a cloud-based system, virtualization plays an important role, and it allows you to run multiple virtual servers on the same physical hardware. So what is this virtualization? Well, if you look at the second block diagram from the left, this is type 1 of virtualization. Virtualization is a process where we create a virtual CPU, a virtual memory, or even virtual networks from physical resources like CPU, memories, and networking hardwares. You can create and enable multiple virtual machines on the same set of hardware. And these all virtual machines can share the same physical resources. This process separates the logical resources from the underlying physical hardware. So this provides more flexibility on the resource management. In general, you can consider that in virtualization, Applications works with the virtual CPUs and virtual memories, etc. And they are treated like they are running on a separate physical machines because their resources are virtually isolated from other machines. In a cloud-based system, you have the hardware layer and on top of it, there is a hypervisor. This hypervisor creates a virtual CPU and virtual storage from the physical hardware. This setup allows you to run multiple virtual machines or VMs on the same physical hardware, and each of them can act like an independent server or an independent machine. And these all virtual machines will have its own operating system and applications. Now, there are two types of hypervisors used in virtualization. If the hypervisor runs directly on the hardware, it is called type 1 hypervisor. If the hypervisor runs on top of a host operating system, then it is called type 2 hypervisor. Even though virtualization is efficient, but these systems can be further optimized. In a virtual machine setup, each VM typically have its own operating system, like Linux or Windows operating system, etc. And if you install a fresh operating system on each individual virtual machine, then it will increase the storage requirement, which is an additional storage overhead on the machine. And when you start a virtual machine or restart your VM, then the operating system will boot up like normal every time. And this can be a time consuming process. To overcome these issues, cloud systems are evolved to use containers, which are more lightweight and efficient than the traditional virtual machines. In this container based system, your application and all of its required elements like libraries, functions, binaries, everything are placed into a single lightweight container. So this will allow faster startup time and better resource utilization. Additionally, you can run multiple containers on a single operating system. So you do not need individual copies of operating system for each container or each application. So this is the example of cloud native applications, where applications are designed and run as containers, and they are also optimized for modern cloud environments. We talked about virtualization, and we learned how virtualization and cloud native technologies can help to evolve 5G requirements. Now we also have some basic understanding of 5G core network. So let's understand their specific core functions. Earlier, we discussed the basic visualization of the 5G network and we've seen its key component. You can also see those key components here. This screenshot highlights the core functions, which is essential to the 5G network operations. Now we have added little more functions in that core network architecture. So you can see some of the newly introduced functions include NEF or network exposure function, NRF or network repository function, and AF or application functions. Each of these functions are capable of adding new capabilities to the network. First, we will explore how these functions are typically visualized in the network architecture. And then we will take a look at the description of these functions. The 5G network can be visualized in two main styles. The first style is reference point representation. In this reference point representation, the interfaces between different network functions is specified as point-to-point connection. You can see that each point-to-point link is defined by the interface name like N7, N8, etc. This is the similar approach like previous generation technology designs like 4G and 3G. So it can easy to relate if you have experience with the previous generation technologies. The second style is called service-based representation. In service-based representation, the core network functions are shown as services, and these functions are interconnected with the labels, which are indicating the service interfaces of each function. This approach aligns better with the service-based architecture of 5G. In this model, any network function can expose its services to the other authorized functions. So they have better flexibility and interoperability. This service based representation is particularly relevant for 5G as it aligns with the network service based architecture, which is the main reason for its flexibility and scalability. Now, let's explore the main role and functions of these various components within the 5G core network. We will start with the NRF or Network Repository function. The 5G core network is composed of various network functions. Each one is designed as a service to ensure the flexibility and scalability. The NRF serves as a central repository that stores the profile of all network functions available in the core network. These profiles contains crucial details such as the type of network function, network address, capacity, and supported services, etc. When a service consumer need to locate a service provider, then it communicates with the NRF to find the necessary address and details. For example, if the AMF want to locate SMF, then it will check with the NRF to retrieve the SMF address and availability. The NRF can also provide information that how many instances of SMF are currently running. Additionally, it can provide details about the SMF capacity and other relevant metrics. And with all this information, service consumer can discover and select the most suitable service provider without needing any pre-configuration. Next, let's discuss the AMF or authentication and mobility function. The AMF is responsible for establishing and maintaining the encrypted signaling connections with the user equipment or UE. This functionality enables the UE to register with the network, authentication, and seamless mobility between different radio cells. The AMF also handles session management signaling between devices and SMF to experience a smooth communication between the network. The AMF communicates with the G Node B through the N2 interface and with the UEs via the N1 interface. Interaction with the other network functions are carried out through the service-based interfaces from the concept of service-based architecture in 5G. Now let's understand SMF or session management function. The SMF is responsible for setting up the connection between the UE and data network. The SMF is a control function that manages user sessions, including their establishment, modification, and termination. And it also handles allocation of IP addresses for IPPDU sessions. The SMF also select and control different network functions over the N4 interface to ensure seamless session management. Additionally, the SMF interacts with the PCF to retrieve policies and configure the UPF accordingly. The SMF is responsible to collect the charging data and it manages the charging functions within the UPF. Next is AUSF or Authentication Server Function. AUSF presents the subscriber home network and handles authentication. It manages authentication by processing the information in the home network and from the received UE data. It retrieves necessary data from the UDM. Next, let's discuss the policy control function or PCF. The PCF is responsible for enforcing policies across various aspects of the network. It provides session management related policies to SMF, like quality of service or QoS requirements. The PCF also collaborates with the SMF to enforce access and mobility related policies, including radio frequency selections, service area restrictions, etc. The PCF interacts with the UE through the AMF to manage the policies, like how the UE should interact with the non-3GPP network, like Wi-Fi, etc., and handle network size selection. Finally, let's take a look at the UDR or User Data Repository and UDM or User Data Management. The UDR stores the subscription data and network related information, while the UDM manages this data to support various network functions. The UDR acts as a database and stores the subscription data and the network configuration information. The UDM serves as a front-end interface and responsible for accessing and managing the subscription data which is stored in the UDR. The UDM uses the subscription data that is stored in the UDR to perform different tasks like generating authentication credentials and managing UE registrations with the network, etc. So in summary, we have learned about two different ways of representing 5G core network and the role of different core network functions to maintain and optimize network operations. Okay, so that's it for today. I hope this short learning series helps you in developing the basic foundation of 5G architecture and core network functions. In the next learning series, we will understand more 5G concept in more details and we will discuss use cases of 5G and new advancements in the technology. So stay tuned for the updates. If this learning series is informative and helpful, then please like the videos, comment on videos, and don't forget to share. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. Thank you for watching.